Good morning, everyone. My name's Aman, and welcome to this GCSE Chemistry session this morning. Today we're going to be doing the session that we were supposed to be doing on Monday, which is polymerization. So we're not going to miss out that session. We are doing it today. And then natural polymers and DNA, which was supposed to be today, will be tomorrow instead. So everything's just being pushed forward. This session will last for 1 hour, so from 9:45 until 10:45. And as usual, if you have any questions, please put them into the chat box or the Q&A function, and I will read them as I'm going along and try and answer them for you. As I said, we'll be covering polymerization, which we did a bit of on Monday, but we'll be looking at it today properly. If you haven't met me before, my name's Aman, and I study medicine at King's College London, and I've done plenty of lessons with MyTutor. So I think we'll get started. So if you were here on Monday, hopefully you remember the learning objectives. So we're going to be trying to draw the diagrams for addition polymerization, which is a core topic. We need to know the uses of some of the polymers, again, a core topic. Explain the disadvantages of polymers, another core topic, and then a higher tier topic, be able to draw the diagrams for condensation polymerization. So addition polymerization is core, condensation polymerization is a higher tier topic, and we'll go into that today. And for those of you wondering, we will be doing a quiz at the end of the session, followed by some exam style questions. So the missed lesson, I'm redoing it today, and everything's just being pushed forward. So I believe the lesson that was supposed to be happening today was natural polymers and DNA, and instead that will happen tomorrow. So everything's being pushed forward one day. Okay, so a quick recap. These are different questions from the ones that we did on Monday if you were here. So does anyone remember the name of the product in the reaction between propene and chlorine? So this is a recap from last week when we were looking at alkenes and alcohols. Does anyone remember what happens between propene and chlorine? Excellent, so we've had, great, so dichloropropane. So for the person that's saying they weren't here on Monday, that's absolutely fine. This is a repeat because Monday's session didn't go ahead. So dichloropropane, excellent, well done. So I'll type that out for you. So the general rule for when we react an alkene with a halogen is it will be halogen, so halo, alkane. So remember, it breaks the double bond, so it becomes an alkane. So in this case, it's dichloropropane. So well done. The next question is asking for the two products when butanol reacts with an oxidizing agent. So butanol is an alcohol, and when it reacts with an oxidizing agent, what do we think is formed? Excellent, so I've had a couple of correct answers. So propanoic acid and water. Butanoic acid and water. So butanoic acid is a carboxylic acid. So butanoic acid and water. So remember, the butanol becomes oxidized. So instead of having an OH bond, which is what happens in an alcohol or what is there in an alcohol, we end up having a COOH bond and water. So it becomes a butanoic acid and water. Which two conditions are needed to react propene with hydrogen? Which two conditions are needed to react propene with hydrogen? So if you were here on Monday, this question was here on Monday, but I've left it in because it's quite important. So great, I've had one answer. Anyone else? Yep, good. So nickel catalyst and 60 degrees, a nickel catalyst and 60 degrees. And you do need to know the conditions for that reaction. Just out of interest, does anyone remember what's formed when we react propene with hydrogen? Does anyone remember what's formed? So this is one of my favorite reactions because I find it the most easy to remember. So propene with hydrogen, what's formed? Excellent, propane. So someone's asking me, how do we remember these reactions, which is a really good question. And I think I was asked it on Monday as well. And the best way that I find is to actually write down the reactants and think about what's happening. So for example, with the first one where we've got propene reacting with chlorine, we know that propene is C3H6, so 3 carbons, 6 hydrogens. And it reacts with chlorine, which is a gas, it goes around as Cl2. So the first thing we know is that there's going to be 2 chlorines adding on to the bond. And the other thing that we know is that with alkenes, we always add on to the double bond. So when we're adding on to the double bond, so if I draw propene here, so this is our propene. Remember, 4 bonds, no more than 4 bonds around carbon, like so. we can see that the chlorine has to add on to this double bond. That's the only place it can add on to. So when the chlorine joins, it comes on here like so. And in order for that to join, we need to break this double bond. So that double bond breaks, becomes a single bond like so. And then to name that product, there's two chlorines, so dichloro, and it's become propane because there's no longer a double bond. So that's how I remember that one. With this one here, so the two products when butanol reacts with an oxidizing agent. So I remember the oxidizing agent essentially just means oxygen's being added, and butanol is an alcohol, so it's looks like this. There's no double bonds in alcohol, but remember there is the OH bond that makes it an alcohol. And if we add oxygen on, essentially what's going to happen is oxygen's going to go into this bond here. And so we end up with a COOH. And the reason for that is that we've added two oxygens. So it becomes a COOH bond, like so. So it's one oxygen that's been added. The OH is essentially stayed. So if you imagine this has been added in a double bond, the way I remember that is that oxygen is bonded in a double bond. So if you remember in covalent bonding, when we try and add oxygen, oxygen has a double bond. It shares two electrons with each other. So we have a double bond there. So there's COOH. And then what's left? Well, if we think about it, when we add in that double bond, we've lost this hydrogen, and there's one more oxygen, because when we add in oxygen, it's O2. This was already there. So we've got one oxygen that's not been added in, because one's here, and we've got two hydrogens that are being lost. So that's H2O. So if you think about it like that when you're doing your reactions, you can always pretty much work out what the products are going to be when you do your reactions. Okay, the next question is give the names of the two products when sodium reacts with methanol. When sodium reacts with methanol. This is a year 11 topic. Is the OH a carboxylic group? OH is an alcohol group. COOH is carboxylic acid. So what are the two products when sodium reacts with methanol? How do you remember it if you don't know the chemical formulas? That's a really good question. So the chemical formulas, the way that I tend to remember them is to know the first four of each of the groups. So if we know that methane is the first one, methane's always one carbon atom. And in an alkane, the general rule is CnH2n plus 2. So if you remember that, then we know we can work out the formula of methane. In an alkene, it's CnH2n. There is no methane, so the first alkene is ethene. And if you just remember the first four of each one and remember the general rule, you can work out the chemical formulae for all of them. It comes with practice, and just keep persevering with it. I know it's quite confusing, and I know it can be quite tedious. There's a lot to learn. But if you keep persevering with it, I'm sure you'll grasp it. Okay, so someone said sodium methoxide and water. So it's not water that's produced, it's hydrogen, but yes, sodium methoxide. And the reason for that is, if you remember methanol, if I draw methanol out, so we've got our CH3OH, so this is methanol. When we add sodium in, the sodium essentially replaces the hydrogen. So it becomes sodium methoxide. And when that sodium replaces that hydrogen, what's being lost is one H. So essentially when we balance the equation, you'll end up with two H's, which is hydrogen. So it's hydrogen that's lost when we react sodium with methanol. So sodium methoxide and hydrogen. Okay, the final question, why are carboxylic acids weak acids? Yes, this is a year 11 topic. So does anyone remember, why are carboxylic acids weak acids? Excellent. So someone said it only partially ionizes. Brilliant. Yep. So remember, most acids will ionize. So specifically with carboxylic acids, we have the COOH group. And what happens is that they ionize into COO minus and H plus. And remember, it's the H plus that makes it acidic. But with COOH, it doesn't really like to ionize. So the position of equilibrium, so if I write it as an equation, it's a reversible reaction. The position of equilibrium tends to lie more to the left, so over here. So there's not much H plus being produced, and that means that it tends to be a weak acid. Whereas an acid like hydrochloric acid, which will ionize into H plus and Cl minus, the position of equilibrium tends to lie over here. So there's lots of H+. So hydrochloric acid will be a strong acid. Are these questions to do with the last lesson? Yep, so they're to do with last Friday's lesson. Good. What is ionizing? Ionizing is breaking up into ions. So ions basically means that something has lost or gained electrons. So we know with H+, it's lost an electron, so it's become positively charged. COO- has gained an electron, so it's become negatively charged, so they are ions. Okay, great. So everyone said that they don't ionize or they partially ionize, which is great. Okay, so let's move on to today's topic then. So first of all, core topic, addition polymerization. And when I went over this on Monday, the way I decided to describe it to you was that most of the plastics that we use today are polymers. So if you think about carrier bags, if you think about cling film, chopping boards that are plastic, all of these tend to be made from plastic, and they are polymers that are used to make them. We'll go through which polymers make which plastics in a couple of slides. So we need to know what a polymer is. Obviously, that's the core topic for today. And what is a polymer? So it's a substance with a high relative formula mass. Does anyone remember what a relative formula mass is? This is AQA, EdXL, and OCR. All three of the exam boards have these topics in. There are some things that swap between them, which again, I've tried to cover all the content for all three exam boards. So what is relative formula mass? Good, it's the total atomic number, and I like that definition. So if you remember when we went over quantitative chemistry a couple of weeks ago, we looked at the relative atomic mass. So on a periodic table, if we look at oxygen, for example, it will have a relative atomic mass on top, which is the number of protons, and then it has the relative, number of neutrons, sorry, plus protons, which is 32 on the bottom. Oh, sorry, hold on. Wrong way around. So it's got the number of protons on top, which is 8, and the number of neutrons and protons on the bottom, which is 16 for oxygen. Sorry. So the relative formula mass, or the relative atomic mass, is 16, and the protons is at the top, which is number 8. So the polymers are made up of high relative formula mass. So what that is that we add up the relative atomic masses of all the elements in the polymer. So for example, one polymer is polyethene, so it's made up of ethene monomers, which is here. Before I go into the relative formula mass of that, does anyone remember what monomer means? Or any ideas? What does monomer mean? Yep, so it's what polymers are made of. So I like to think of it as the repeating unit. So in polyethene, it's made up of lots of ethene molecules. So it's the repeating unit. The monomer is almost, the single repeating unit. So yeah, really great definitions that are coming through. Great. So in polyethene, we add up lots of ethenes together. They join together. And so the relative formula mass will be all the ethene molecules added up. So the carbon's all added up, the hydrogen's all added up. So for example, we know that the relative atomic mass of carbon is 12 and the relative atomic mass of hydrogen is 1. So each carbon will have a relative atomic mass of 12 and each hydrogen will have 1. And we add up all the carbons times by 12, we add up all the hydrogens and times by 1. And you add that all up and you will get the relative formula mass. Now, because polymers tend to join up lots of monomers, they tend to have a very high relative formula mass. Another example of a polymer is when we have monomers of chloroethene. Again, I'm going to go into this on the next slide and draw it out for you. And they join to form polychloroethene. So the one thing I want to just point out on this slide is usually when we have lots of alkenes joining together, we break the double bond, which is what happens in polymers, but we end up changing this to ethane. Does anyone know why we don't change it in polymers? Why does it stay as polyethene and not change to polyethane? Yeah, it's still an alkene. Excellent, well done. So it stays as an alkene just because we're joining the alkenes together. It stays as an alkene. We're not actually going to add anything to it to make it become an alkane. So it actually stays as an alkene, which is excellent. Yep. So someone's just asking me to repeat something. I assume it's about the high relative formula mass. So I'll just go through that again, and I'll show it on the next slide as well. So when lots of ethene molecules join together, so remember ethene is C2H4, when they join together, essentially we end up with lots of carbons and lots of hydrogens. And polymers are made up of lots of ethene molecules, for example, for polyethene. And so what that means is that the relative formula mass, or the number of carbons and hydrogens in there, are quite a lot, and that means that they have a high relative formula mass. So when we're working out the relative formula mass, we look at the number of carbon atoms, we multiply by the relative atomic mass of carbon, which is 12, and then we add that to the relative atomic mass of hydrogen multiplied by how many hydrogens there are. So for example, if in one polymer we had, let's just say 12 carbons, then we would do 12 times 12, which is 144 for the relative atomic mass of carbon. And then let's just say it had 20 hydrogens. Again, this is just an example. And that means then that there would be 20 for the relative formula mass of hydrogen. So we add those together and we get 164. So the relative formula mass of the polymer would be 164, which is quite a high relative formula mass. Usually they're a lot bigger than that because polymers tend to be made of lots and lots of ethene molecules, or polychloroethene, so lots and lots of alkenes. So this reaction where we add lots of alkenes in to make a polymer is called addition polymerization. And essentially what's happening is that the double covalent bond is broken to allow molecules to join to form a single product, the polymer. If you're wondering about what the conditions are for this reaction, you don't need to know them, but just out of interest, if people do want to know, it tends to be about 60 degrees, and you tend to have a catalyst in there as well. So 60 degrees and a catalyst will be there as well. You don't need to know which catalyst it is. It's something that you learn at A level. Okay, so any questions on this slide at all? Anything that you want to ask? If not, we'll try and draw some on the next slide. So someone's just asked me what Mentimeter is. We'll be doing a quiz on Mentimeter today. It's essentially a quiz software and it's free to use. So I'll show you that later on today. Okay, great. So there's no questions on this slide. So let's try and draw some polymers then. So this is essentially what they're probably going to ask you to do in the exam. They're going to ask you to draw the polymers. And the most common one they ask you to draw is ethene because it's the first polymer. So let's just imagine then we've got lots of ethene molecules. So remember we've got our double bond and 4 hydrogens. And then let's add that to another one. And one more. Okay, so to join these together, what we can see is that this double bond here and here and here needs to break, because if we want to join them together, we need to be able to form a bond like this and like this. And to do that then, the carbon needs to have a bond available. At the moment, if we look at each ethene molecule, because of the double bond, carbon's already made its 4 bonds. It's got 2 with 1 carbon, 1 with hydrogen, and another one with hydrogen, which makes 4. So for it to join to another ethene molecule, that carbon double bond needs to be broken in order to allow a 4th bond to happen with another carbon. So that's what happens when we polymerize. We break that double bond, but because we've not added anything in like hydrogen, it still stays as an alkene. So the monomers are still alkenes. And what's really important in the exam is you wouldn't need to draw out lots of ethene molecules joining up. You need to be able to draw the repeating unit. So if I draw lots of them together, so we know that that carbon bond breaks. So this is our 6 carbons, our hydrogens. So what we can see, it is looking like an alkane at the moment. But what happens is it continues going on and on. So I'm just going to remove this hydrogen. I drew 3 alkenes. But remember that no hydrogen's been added. So on this last carbon here, because no hydrogen's been added, it's not going to have that 4th hydrogen bond, which would make it an alkane. Instead, it's going to look a bit like that, where it continues on with polymers. So remember, there'll be lots and lots of ethene molecules. So the key thing in the exam is to draw the repeating unit. So the repeating unit in ethene is essentially 2 carbon atoms and their hydrogens. So it's this. And you can see that's repeated 3 times where I've drawn it. And when you draw a repeating unit, you always do square brackets. We're going to have the 2 carbon atoms that would be in 1 ethene molecule. The 4 hydrogens, we've not added any hydrogens, so it's going to stay as 4. And then what you do is you draw a bond going through the square bracket to show that that continues on. to show that there could be more ethene molecules either side. And then we do an N here. And that N represents that there could be lots and lots of ethene molecules. We don't know how many. If in the exam they say 10, then you would make that N a 10. But usually we just write an N. And that is the repeating unit for polyethene, or polythene, which is another name for polyethene. Someone's just asking me about Mentimeter again. They're asking, is it like Kahoot? So Kahoot tends to show the question on my screen and you guys answer on your screen. Mentimeter will show the question on both of our screens. So I'll show you later when we do it. So does it stay unsaturated when it polymerizes? Yes, it's a tricky question to answer, but essentially yes, but they're very unreactive. So because they don't technically have that double bond in there, they're very unreactive. So that's the repeating unit of polyethene. Let's now draw the repeating unit of polypropene. And this is a little bit trickier to understand, but the way I try and remember it is that we're breaking carbon double bonds. So remember, propene is 3 carbons. Again, remember to always only draw 4 bonds, so just count up as you're going along to make sure you don't draw any extra. So 4 there, 4 there. So that's our polypropene. Now, you might be thinking, well, where's the repeating unit? And essentially, it's going to look a little bit like ethene. Because we break this double bond, when we add in another propene, the propene molecule will join to this double bond, which means that we actually need to change the structure of propene. And it doesn't change much. What happens is it looks like this. So we still have our H's like so. And then we have one H here. But because another propene wants to join on to this double bond, essentially the propene's got to join here where it wants to join. Let's just say that. Obviously the double bond will break. So this CH3 goes down here. It's still there, but all we've done is we've put the bond here instead. So when we're drawing the polymers of alkenes that have higher numbers, so propene, butene, pentene, we always put them down below so that the new monomer can join on to the double bond. It's not changed the structure. All I've done is move this carbon down here instead. I've not put it on the right. And that then means that the repeating unit for propene looks like this. That's just the CH3. Sorry, let me just get rid of that double bond. Like that. So that's the repeating unit of propene. So I've just moved this hydrogen down here, like that. And all that's happened is that the propene, or the third carbon, is moved down below. So if I do the same for butene, which would be polybutene now, again, butene has a double bond and then it's got 2 carbons, like so. And again, when we add on monomers for butene, it wants to add on to the double bond. So essentially what we need to do is we need to move this down below. So again, the repeating unit, if you imagine this is the double bond here, I've just broken it, are 2 hydrogens from the first carbon. The second carbon has 1 hydrogen on top, and then we just need to move all of this down below. So this is C2H5, so we put it down below, C2H5, and then our square brackets, like so, and then don't forget the N as well. So that's butene. So essentially, if you just remember that the monomers are being added on to the double bond, then hopefully it will make sense, and you've just got to move anything else onto the other carbon atom. Someone's saying, why is chemistry so complicated sometimes? I agree, chemistry is complicated, but the way that I try and do things is just keep repeating, going over things. Anything that you find difficult, I like to write post-it notes and stick them in my room, and so that I keep kind of being exposed to them and looking at them, and that just makes it a little bit easier for me to understand. But I definitely agree. I think chemistry is one of the harder sciences, but again, just keep doing a little bit every day and hopefully it will start to make sense. And that's what worked for me when I was doing my exams. Okay, so the final one then that we need to draw is chloroethene, which is nice and easy. The only difference is with chloroethene, it's essentially ethene, but one of the hydrogens is a chlorine. So it's like that. So that's chloroethene. So again, the repeating unit looks exactly the same as ethene, just with one hydrogen being a chlorine. So it will look like this. So hydrogen, hydrogen, chlorine, hydrogen. So the main rules about drawing a polymer is to have square brackets. Make sure you have lines going outside the square brackets, which represents that more monomers can be added on. The double bond is broken, but you will essentially have 4 bonds. So what you can see is this is 1 bond, this is a second, this is a third, this is a fourth. So you don't draw the 4th hydrogen, you draw it as a bond going through. So there's still 4 bonds there. So hopefully that makes sense. Anyone got any questions about how to draw polymers? I've tried to draw a couple there. So if you just remember how to draw the repeating units of a couple, hopefully it will make sense. How different is A-level chemistry compared to GCSE? If I'm being honest, I think it's quite a big step up. It is quite a big step up, but I really enjoyed it. I thought A-level chemistry was really, really interesting. Can you give an example to replace the N? Yeah, so it's just, if for example, so I saw an exam question the other day where they said there were 1,000 ethene molecules. So all you needed to do was replace this N with 1,000, nothing else. You don't need to draw it out, you just put 1,000 there. But usually they won't tell you how many molecules, so you put an N to just represent there could be lots and lots. So for my A-levels, I took chemistry, biology, Latin, and maths. Okay, so let's move on then to some of the uses of polymers. So these are the 4 polymers that you need to know about. For AQA, it seems that you only need to know about the first 2. For EdXL and OCR, I think you need to know about all 4. But I mean, they're not too difficult to remember if you've got something where you're living at the moment. I try and kind of relate it to that. So for me, the easiest one to remember is polythene or polyethene. It's flexible, strong, easy to shape and cheap. And I think of carrier bags and cling film. So if you imagine carrier bags and cling film, quite flexible, quite flimsy, quite easy. So they're easy to shape and they're quite cheap as well. So that's polyethene. So that's how I remember those ones. Polypropene or polypropylene, which is another name for it, tends to be a bit tougher. So things like ropes, milk crates, so carpets, which is probably a bit surprising, but some carpet fibers are made for plastics. Someone saying bad for the environment. Yep, excellent. We're going to get onto that in the next slide. PVC. So the way I remember PVC is to remember it's an electrical insulator. That tends to be the only property I remember. And then I just remember that it's an insulator for electrical wires because it's an electrical insulator. So it doesn't make the wires, it's an insulator for those wires. And the 4th one, polyfluorotetraethylene. I will draw this one out in just a second because that is one that I didn't draw out. This one tends to be unreactive. So I think of non-stick pans. So if any of you like to cook, you might know that some pans tend to have non-stick on them to stop food sticking to the bottom. That tends to be made from PFTE or polytetrafluoroethylene. I will just draw that out. Again, it's nice and easy. It's just an ethene molecule, but instead of having hydrogens, it's got tetra, which means 4 fluorines. So it's just 4 fluorines added on instead. So that's essentially the molecule. And then when you draw the polymer for it, again, square brackets, break the carbon bond and just put the 4 fluorines on, like so. So that is polytetrafluoroethene. Any questions on the properties or on their uses? What does tetra stand for? So tetra doesn't stand for anything, it just means 4. So you know how di, for example, meant 2, tri means 3, tetra is 4. Yeah, tetra is 4. Good. Do you need to know the chemical formulae? No, so there's not really a chemical formula for polymers. All you would be asked to do is draw out the repeating unit, which is the square brackets. Okay, so do we need to know how to draw the structures of these polymers? So from the exam questions I've seen, the ones that they always ask about is polyethene. So I would make sure you know how to draw polyethene, which I think is the easiest one to draw. It's just this down here, polyethene. I would, if you are doing the higher tier, I would make sure that you know how to draw some of the others as well. The 4 most common ones I've drawn, so polyethene, polypropene, polychloroethene and polytetrafluoroethene I've drawn for you. I also drew polybutene as well. How do you remember the square brackets? Because they're the only reaction that requires square brackets. So that's how I remember it. Yep. Great. So someone said penta is 5, hexa is 6. So yeah, well done. Okay, let's move on then. So to some of the disadvantages of polymers, again, really important that we know about them. So they're unreactive, making them difficult to dispose of, and that's because the double bond's been broken. So remember, the double bond in alkenes makes them quite reactive. There's lots of electrons in that double bond, and they essentially want to react. But in polymers, because that double bond's been broken and they're quite stable as polymers, they don't tend to want to react, which makes them difficult to dispose of. Non-biodegradable. Does anyone know what biodegradable means and what usually happens if something is biodegradable, or what that means? Someone's just asked me, what does finite mean? I'm going to come to that in just a second. Good. So non-biodegradable essentially means it cannot be broken down, but the way that it would be broken down if it was biodegradable is that microorganisms would come in and, if you like, eat the plastic. But because it's non-biodegradable, microorganisms cannot do that. So that often means that plastics will end up in landfill sites and they won't break down, they won't decompose, and that obviously uses up our landfill sites. Incineration releases carbon dioxide. So if you remember last week, we went through loads and loads of combustion reactions of all the different groups. Polymers do combust almost, or they burn, and that releases carbon dioxide. And what's the danger with carbon dioxide? Why don't we like carbon dioxide being released? What's the problem with carbon dioxide? Yep, it's a greenhouse gas. It contributes to global warming, climate change. Excellent, all really great answers. Well done. Is incineration the same as combustion? So almost. So incineration is actually burning. Combustion is just reacting with oxygen in a burning type reaction. So you don't need to know the combustion reactions of polymers. Incineration essentially means setting it on fire and burning it. Okay, finite then. So what does finite mean? Anyone know what does finite mean? So someone's asked me. Yeah, it will finish. That's a really good way to remember it. So it will finish at some point. It will run out at some point. Good. It's non-renewable. Why are polymers non-renewable? What is it that makes them non-renewable? Someone's asking, what is the food waste bag made of? I don't know where you live, but where I live, it's actually made out of plastic. So I don't think it can be decomposed. Some of them are being made of plastics that can be. So they won't tend to be the polymers that we've looked at. So yeah, it depends where you live, I think. So in London, as far as I'm aware, the plastics are not biodegradable. Good, right, so someone's given me a great answer. So for the finite resource, it's made out of hydrocarbons, which is crude oil, which is finite or non-renewable. Yep, really good answer. So remember then that crude oil, we fractionally distillate it, or we do fractional distillation to make it into smaller fractions, because the crude oil is a mixture. We need to separate that mixture. We then do cracking to the crude oil or to the fractions of crude oil to make our alkenes. And remember, polymers are made of alkenes. So that means that the polymers have come from crude oil, which is going to run out eventually. So it's a finite resource. And then finally, recycling. So it used to be a big topic kind of in the old GCSE syllabus. They still tend to ask about it, and you do need to know about recycling. So with recycling, although it's a great thing, there is a lot of energy wasted. So first of all, the polymers have to be melted to be recycled. That requires energy. The second thing is actually to separate polymers. So a lot of different polymers are made of different things. We've got polytetrafluoroethene, we've got polychloroethene. They're different polymers. We can't melt them all together. We need to separate them. And that takes time, which often means it's actually quite hard to recycle polymers. So there's kind of advantages and disadvantages with recycling. Although yes, it's good for the environment in the sense that we're reusing things, it is bad that we need to use energy to melt them, and also to separate polymers can be quite a lot of work. Good. Any questions on the disadvantages then of polymers? If not, we'll go on to the last learning objective of today, which is condensation polymerization, which is a higher tier topic. So fractional distillation, we covered that on last Monday, I think. So if you go back to that lesson, hopefully that will help. Okay, so let's move on to condensation polymerization then. So condensation polymerization is a higher tier topic, as I said, and it's used to make polyesters and nylon. So from what I gathered from all of the exam boards, it seems that they most of the exam boards only want you to know how to make polyesters. Nylon, you need to know about that it is made from condensation polymerization, but you don't need to know how it's made. You do need to know how polyesters are made. So before we go into what a polyester is, does anyone remember how we make an ester? How do we make an ester? So if you were looking at last week, how do we make an ester? Anyone remember how we make an ester? Excellent. So someone said carboxylic acid and alcohol. Brilliant. Yeah. So carboxylic acid and alcohol. So it's the same with making a polyester. We still need to use a carboxylic acid and an alcohol. And does anyone remember when we make an ester, what's the other thing that's formed? So we get an ester and something else. When we react an alcohol and carboxylic acid, we get an ester and one other molecule. Does anyone remember what it is? Water. Brilliant. So in condensation polymerization, the reason it's called that is because water is released. Sometimes you get a different molecule, such as hydrogen chloride, but usually it's water that's released. And all the reactions we're going to look at will release water. So condensation polymerization is different from addition polymerization in that another molecule is released. So when we did addition polymerization, you saw that we were breaking the carbon double bonds, but nothing else was being produced. You were just forming from the monomers a polymer. In condensation polymerization, you form a polymer and something else. And the way I remember this is to remember how esters are being formed, so from an alcohol and a carboxylic acid. And if you remember that, you'll remember how polyesters are formed, because they're formed from dicarboxylic acids and diols, which I'm going to draw in just a second. So as I said, condensation polymerization makes polyesters and nylon. You need to know about polyesters specifically. We're going to watch a video in just a second on how nylon's produced, just to show you that you can actually do it in the classroom. And I'm sure some of you might do it next year when you go back to school. Any questions so far on this reaction or not? If not, I'm going to draw it. So it seems very rare that they ask you to draw these reactions. It seems more that they ask you how a polyester is formed, what are the monomers. But they're quite easy to draw if you remember the general rule. So I'm going to show you the general rule just because you do still need to know about it. So I said that there's dicarboxylic acids and diols. So let's take ethane diol. So ethane diol. So ethane has two carbons. So, oh, that's interesting. Okay. Okay, so can you all see the screen? Just out of interest. Okay, Tilly.
Hi, is everything okay?
It's not letting me draw on the screen or type on the screen.
Oh, strange. Will you be able to leave and rejoin the lesson space?
No, because we don't have another free meeting. I don't think it will let me do that.
Okay, just bear with me 1 second.
It's fine if not, I can just talk through it.
Have you tried switching to another one of your pages on the lesson space itself?
Oh, it's letting me touch the lesson space, but it's not letting me, let me see. Yeah, it's not letting me draw.
Do you think you'll be able to talk through the rest of it?
Yeah, that's fine. That's the last slide anyway. Okay, so as I said, a dicarboxylic acid and a diol make an ester. So you don't really need to know how to draw it. And what I will do is tomorrow's lesson at the beginning, I will draw it out for you. But for today, I'm just going to explain it. So a dicarboxylic acid could be something like hexane dioic acid. And what that means is that on each end of the hexane molecule, you will have a COOH group, which is the carboxylic acid group. And then the diol will have an alcohol group on each end. So if you imagine ethanol, instead of having an OH group on one end, it will have it on both ends. So these join up to form a polyester. And as I said, I'm going to draw it for you tomorrow properly so you can see it. But for now, I'm just going to talk through it. So a dicarboxylic acid and a diol join up to form a polyester. And that's essentially all you need to know. And you wouldn't ever be asked to kind of draw it out. You'd be asked to draw out the general kind of formula for it, which I'll show you tomorrow, which is a lot easier to draw out than trying to draw out all the carbon atoms, for example. So let's watch a video then on nylon. See if I can get this to play. Hopefully it will play. Okay, so hopefully you can see this now. So this is making nylon, which is made from a diamine. So this is our diamine and a dicarboxylic acid, which is over here. So we've got a diamine and a dicarboxylic acid. So we're adding that amine to the dicarboxylic acid. So nylon's not made like a polyester. It isn't a polyester. It's something different. The solutions are immiscible, which means that they don't mix. So if you imagine trying to do water and oil, they don't mix. But what's happening is, as this says, on the interface between the surfaces, so where the surfaces kind of collide or join, nylon's being produced, which you can see now. So that's the nylon, and there we go. So this tends to be a school experiment that you might do, and you can see the nylon being produced there. And again, that's another condensation polymerization polymer, which is nylon, and as it says, it's a polycondensation reaction going on, or condensation polymerization reaction. Great, okay. Any questions then on condensation polymerization? No? Okay, so let's do a mentee quiz then. So it's going to be a quiz covering everything we've covered today. Before we go on to the quiz, if I just take us back to the learning objectives. So I drew for you the diagrams of addition polymerization, and we went through how those reactions take place. We went through the uses of some of the polymers, and we explained the disadvantages of the polymers. And I haven't been able to draw the condensation polymerization reactions for you, but I've explained it to you, and I will draw it for you tomorrow. As I said, for some reason, it's not letting me draw on the screen. Okay, so let's do the mentee quiz. So if you go to mentee.com, and the code is 687201, 687201. So if you go to mentee.com, 687201. What can you do with nylon? Nylon tends to make a lot of clothes. So it's a bit like wool, but not quite, but it tends to make a lot of clothes. Yeah, great. So I can see lots of people joining. So 687201, if you go to mentee.com, it doesn't ask you to make an account. It's completely free to use. Great. So I'll just wait a couple of minutes for more people to join. I think there's 5 questions, and at the end, I think there's a Q&A function, so you can actually type questions in at the end for me if you've got questions about the quiz. But as I'm going along, I'll try and answer the questions. Great, so there seems to be lots of people joining. Okay, so there's 30 people in the webinar, and there's 18 on the quiz. So I'll just wait another 10-20 seconds and then I'll start it. And I think you can join halfway through. So if you're struggling to join, you should be able to join about halfway through. Okay, fine, let's start it then. So the first question should be coming up on the screen now. So which polymer is formed from the monomer pentene? So you have to type in the answer, which polymer is formed from the monomer pentene? So remember how we named them. So we didn't go through pentene, but you do need to know how to name the monomers. Remember, they stay as alkenes. That's a clue as well. So the answer is polypentene. Great. So most people gave polypentene. So it's not polythene. Polythene is polyethene that comes from the monomer ethene. It's not a polyester. Polyesters are made from dicarboxylic acids and diols. And as I said, it's not polyethene. So yeah, the answer is polypentene, and you can write it like this as well with the brackets. It's up to you, however you want to write it. Okay. The next question, it should be coming up in just a second. So what is PVC used for? So this is polychloroethene. That's another name for it. Does anyone remember what is PVC used for? So it's a multiple choice question, so you should just be able to click one of the answers. Okay, so the answer is insulation for electrical wires. Great, yep, most of you got that, really well done. So cling film is polyethene, carpets is polypropylene, and non-stick coating is polytetrafluoroethene. Great, so the next question, it should be coming up in just a second. Why are polymers difficult to dispose of? Why are polymers difficult to dispose of? So some of these are properties of polymers, but it doesn't necessarily make them difficult to dispose of. So just remember what the question is and then try and see which one actually answers that question. Great, so the answer is unreactive. Okay, so they are recyclable. It's just difficult to recycle them because we have to separate them. They require energy to melt them. So they are recyclable. We can incinerate them, but it produces carbon dioxide. And they are a finite resource, but that doesn't make them difficult to dispose of. The thing that makes them difficult to dispose of is the fact that they're unreactive. Okay, so the next question should be coming up in just a second. How do we make a polyester? How do we make a polyester? So is it an alcohol and carboxylic acid, an alkene and an alkane and a diol, or a diol and a dicarboxylic acid? So a diol is a dialcohol molecule. So what do we think? So this is what we just covered now with condensation, polymerization. So the answer is diol and dicarboxylic acid. Excellent. Yep. So this is how to make an ester, alcohol and carboxylic acid. A polyester is made from a diol and dicarboxylic acid. Alkene and alkane don't really react together, and an alkane and diol isn't correct either. It's a diol and a dicarboxylic acid. Okay, so there's, I think, one more question. Which polymer is used to make plastic carrier bags? Which polymer is used to make plastic carrier bags? So you have to type in the answer. So remember, we covered 4. So we covered PVC, polytetrafluoroethene, polyethene, and polypropylene. So whichever one you think was the one that was used to make plastic carrier bags, type in the answer for. Okay, so we've got 3 seconds left. So the answer is polyethene or polythene. Great. So some people said polythene, so that's another name for polyethene. Yep, so the correct answer is polyethene. Great, well done. Okay, so let's have a look at the leaderboard. So well done, everyone. You all did really well. Thanks for this person. That's nice of you. So well done, Frosty. Okay. So if you've got any questions, I think you should be able to type them into the Mentee now, and you can ask them. If not, you can put them into the Q&A function, and then we'll do some exam questions. So if anyone's got any questions, put them into the Q&A box, or you could type them into the Mentee if you've got any questions. I'll just wait a minute for any questions. Okay, I'm not sure what this means, pentaethene. So I'm not sure what you're asking me there, but that is not a molecule. Okay. Okay, fine. I'm just going to ignore that one. All right, great. So we'll end the Mentee quiz there and go back to today's lesson. So, okay. All right. So again, this is a bit of a repeat of what we covered last week, but it's to do with polymers. So these are exam questions. These are a mix of AQA and edXL exam questions. So crude oil is a mixture of a very large number of compounds. The name for compounds that contain only hydrogen and carbon is what? What's the answer to that question? Good. Yep, I've had one correct answer. Anyone else know? What's the name for compounds that contain only hydrogen and carbon? Good. It's hydrocarbon. Hydrocarbon. Well done. So it contains only hydrogen and carbon, so we call it a hydrocarbon. The process of separating crude oil is fractional what? Fractional what? The process of separating crude oil. Fractional what? Good. Fractional distillation. Excellent. The process taking place at A. So what's happening at A? So we're heating that crude oil up. So what's happening to it? Okay, so I've had mixed answers. I've had evaporation and condensation. So which one happens when we heat something up? Good, it's evaporating. Excellent, well done. So when we heat something up, it evaporates. Excellent. Okay, so what's happening at B then? So now we're in cold water. We've got our evaporated liquid, so it's a gas. We go into cold water, then what happens? Excellent, yep, it condenses or condensation. Good, so it condenses. So it evaporates at A and condenses at B. Excellent, well done everyone. Okay. That's interesting. The screen has gone blank. Let me just try and see if I can upload the questions again. Okay, fine. Tilly.
Hi.
It seems that the lesson space is not now showing my exam questions. I can see the pages for them, but they're not coming up on the screen.
Are you able to open them separately at all?
Yeah, I can actually.
Yeah, that might be best. I'm not sure what's going on with the lesson space.
Okay. All right, let me just. Oops. Okay. Okay, so hopefully now you can see the second question on the screen. So one of the compounds in crude oil is hexane. The displayed structure of hexane is shown in figure 2. Each line between the atoms in hexane represents a covalent what? Covalent what? Bond. Yep, excellent. Great. What's the chemical formula for hexane? So we've got C6H what? Hexane, it's an alkane, not an alkene. Good, C6H14. So the people that gave me H12, remember it's an alkane, not an alkene. If it was an alkene, it would be C6H12, but because it's an alkane, it's C6H14. Hexane can be broken down into smaller molecules by a process called what? Does anyone remember? After fractional distillation, what do we do? Cracking, excellent, well done, cracking. Okay, what's the polymer made from butene? What do we call that? The polymer made from butene. Good, I've had a couple of correct answers. Anyone else want to answer? What's the polymer made from butene? So this is directly related to what we covered today. Good, yep. Polybutene, well done, everyone that gave me the correct answer there. So polybutene, you can either write that as one word, polybutene, or you can write it as poly and then brackets around the butene. It's up to you how you write it. But yeah, write it, make sure you try and write it as one word, so it's not two words. So polybutene or poly, open bracket, butene, close bracket. Okay, incinerators are used to burn waste polymers such as plastic bags. Tick one advantage and one disadvantage of burning plastic bags. So what do we think? What's an advantage and what's a disadvantage? If we burn plastic bags. So I actually think the advantage is the harder one to realise in this question. So what do we think? Which one's the advantage? Which one's the disadvantage? Yep, excellent, good. So someone's giving me the correct answers. We'll wait for a couple more answers. Okay, so we're only ticking one advantage and one disadvantage. So energy being released is an advantage. We like it when energy is released, we can use it for different things. More recycling is needed isn't relevant because when we burn plastic bags, it's not really relevant, but carbon dioxide being produced is a disadvantage. So when we burn them, we know that contributes to global warming. So that's a disadvantage of carbon dioxide being produced when we burn polymers. So more recycling needed isn't relevant. So you needed a tick at energy release and a tick at carbon dioxide being produced for disadvantage. Good. Any questions on that? Yep, good. So everyone's given me the correct answer. Okay, so crude oil is used to make plastics. So we can see the whole process there. So we have crude oil, heat for distillation. It's usually the naphtha fraction, which is then cracked to make molecules of an alkene. Then we heat it for polymerization. How do alkene molecules form a molecule of a plastic? So essentially they're asking you, how does polymerization take place? Now there's a very key answer that you need to give here that all the exam boards want. Does anyone know what's the answer, or what do we think is the answer for why or how alkene molecules make a plastic? Any ideas? Okay, so monomers of alkenes join together. Yes, so that essentially defines polymerization, but it's not what they're looking for. What's actually happening when polymerization takes place? Yes, it's addition polymerization. Again, not what they're looking for. What's happening? When the monomers join on, what's happening to the alkene molecule? Good, the double bond breaks. So the answer to this question is that the double bond or the double covalent bond breaks to then allow monomers of the alkenes to join together to form a polymer. So what most of the exam boards are looking for is that the double bond is breaking to allow polymerization to take place. What do we think? Suggests one of the main costs of making a plastic from crude oil. What do we think? What could be one of the main costs? Lots of different costs, but any ideas? Good, yep. So energy, heat costs, yep. That's one of the main things. So when we do fractional distillation, when we do cracking, polymerization, we always need energy. That's expensive. Anything else? What else could be a cost? Good. So apart from energy, there's also labor costs. So people actually have to do this. So there could be labor costs involved. Good. Good. Actually extracting the crude oil. Excellent. Yep. Well done. Suggest 2 problems caused by the disposal of plastic in landfill sites. What do we think? What are the problems with the disposal of plastics or polymers in landfill sites? Good. Yeah, it's damaging the environment, which animals need. Yeah, I would agree with that one. It's not biodegradable. Yep, so it uses up landfill sites. Yep, so one of the main answers there is that landfill sites get used up. So that obviously reduces the amount of land that we have. Good. You can also talk about it being damaging for the environment. Good. Yeah, I like those answers. Well done. Okay, so how are hydrocarbons cracked? Does anyone remember? How are they cracked? So we went through this. There are 2 types of cracking. Good. Yep. So someone said there's steam or catalytic cracking. So you'd get 1 mark for mentioning those. We need 1 mark to explain one of them. Good. So the way I would answer this is either to say that a lot of energy is needed and steam. So remember that, or less energy is needed and a catalyst to crack. So remember, there are the 2 types of cracking. When you need steam, it usually tends to be 300 degrees and steam. When you use a catalyst, it tends to be less energy and a catalyst. Okay. Electrolysis of sodium chloride solution produces chlorine. Ethene from stage 1 is then reacted with this chlorine. One of the hydrogen atoms in each ethene molecule is replaced by a chlorine atom to produce vinyl chloride. Complete the chemical equation by writing in the formula of the product vinyl chloride. So the way I would do this is to have a look at what's already been removed. So 1 chlorine has been removed. So we know 1 chlorine is going to be in the product and 1 hydrogen has been removed. So what is the other product then? What are we left with? That's how I would do that question. Good. Yep, someone's given me the right answer. Anyone else want to have a go? What do we think? Yep, good. Good. So the answer is C2. So C2, H3, H3 because one of the hydrogens is in the hydrochloric acid, Cl. So C2, H3, Cl. So everyone that gave me that answer, very well done. Okay, so we'll finish there for today. Very well done, everyone. As I said, sorry that I couldn't show you the condensation polymerization. I will show you that tomorrow morning before we then go into doing natural polymers and DNA. So it's quite biology heavy tomorrow. That's what I would say. It's not much chemistry, it's quite biology heavy. Does it matter what order it's in? Not really, but with these organic chemistry molecules, we always tend to write the carbons, then the hydrogens, and then whatever else is there. Okay, take care everyone, and I will see you tomorrow morning. As I said, quite biology heavy tomorrow. If anyone's got a science joke, you can do the science joke. I don't have one. So if anyone's got one, you can send me one and I'll read it out. But if not, we will finish there. All right then, take care. See you tomorrow. Bye.